All right, testing, great. Okay, so this is joint work with a bunch of wonderful co-authors. Okay, so this talk and this paper are about data. We've all heard many success stories about data recently, right? Data changed my life, data got me a job, data introduced me to my husband, so on and so forth. But what happens when our inputs turn against us, right? What happens when data goes rogue? That's the subject of this talk. And we've actually seen, so it seems like about half of EC so far has been about these problems when our data is coming from strategic players or adversaries in some sense. Okay, and we need to do some sort of learning or inference on data in strategic settings. Okay, in particular, so what's classification? In classification, you have a bunch of data, you feed it to the algorithm, and it learns to classify this data into two categories. So the running example I'll think of is emails, classified as, say, spam or not spam. Okay. In the strategic classification problem, which is relatively recent but really exciting area, this data is coming from agents. Okay, and they may be modifying this data in some way in order to influence how we classify it. And we want to design algorithms that do well in the presence of strategic behavior. Okay, so this is how I picture this strategic classification happening in the context of our paper. So if there were no spam filter, there'd be some sets of emails out there, and we can represent them as points in real R to the D. Some are honest, blue, some are dishonest, or spam, red. Okay, and so if you looked at this data, you would deploy some spam filter, which let's say is a hyperplane, such that points on one side are classified as honest and on the other side as spam. Okay, but of course, if you actually did this, this is where strategic behavior comes in. The spammers would start modifying the emails they send. Okay, and you'd have to respond to that, and then hopefully, intuitively, you'd reach some sort of equilibrium, right, between the spammers and this filter. Okay, so we're trying to capture that problem, and others have as well. I'll tell you about it. But just at a high level, the kind of model we're thinking of is this online model. So over a sequence of rounds, emails will arrive, and we'll use x hat t to denote the features of the email that we see. And I think of that as a point in R to the D. So what the system knows. And it has to classify it as being an honest email or a spam email. And it has some current classifier, beta. Okay, but then the system will get to observe what it should have done. Okay, whether that was truly spam or an honest email. So this is an assumption we'll make. And of course, we think this should happen eventually because the user will say, okay, this was marked as spam, right? Or they'll look in their spam folder and mark it as not spam. For the purposes of theory, we assume this will happen instantaneously as soon as after the email arrives. And then the next email will arrive. Okay. Of course, you could relax that. Okay, and of course, the challenge is the spammers are going to respond to the classifier. So the kinds of features we see here will depend on what we're choosing to do. Okay, good. So there's a couple of most closely related prior works. So in our work, and yeah, good. Yes, so we're going to assume this sort of worst case where the spammer knows everything we're doing. So as soon as we deploy a classifier, they know it exactly. Maybe we publish it. Yeah. We don't want to rely on obscurity, let's say. Oh, good. So in this work and the closely related prior works, the kinds of spam or the kinds of manipulation that we're allowing are manipulating these features X, but not the labels Y. Right, so we're observing that we observed the true Y. Okay, and you've seen there are previous papers where the opposite was true. So, in the literature, both are considered. But in the most closely related works, which have the same kind of model, you're given a fixed data set, and you know the spammer's preferences. Okay, and so then you just want to learn this hypothesis beta that will perform well against new data. So it should classify well on this distribution. In a sort of Stackelberg equilibrium, this kind of leader-follower equilibrium, where I propose a beta, and then the spammers will best respond to it. And I should have chosen beta optimally, knowing that they're going to best respond. Right? Okay, so in this work, we wanted to change some of those assumptions. So the key goals, first, we were interested in this idea of online arrivals. Okay, and so we need a new measure of performance, which we'll use regret, and I'll tell you about it. We wanted to allow these agents to be heterogeneous. So in the previous works, the spammers all preferred the same thing, All the manipulators preferred the same thing. And we also don't want to have to assume that we know these exact preferences or utility functions of the spammers we're facing. Okay. And so that's the idea behind our title. So strategic classification from revealed preferences. We just have to infer their preferences from how these agents are acting. Okay, so the high-level questions we want to address are, how should we model this problem in a way that it's solvable, ideally? What's a benchmark? So what are you shooting for? How do you measure how good an algorithm is? And then how do you design algorithms? Okay, and I'm going to focus a lot in this talk on the first two and show how we can use learning algorithms at the end to solve it when we set these up carefully. Okay, so here's the model in a bit more detail. And I'm going to tell you a very broad model, a very general model. We're not going to solve it in full generality. We're going to make some very strong assumptions later. But I want to emphasize this sort of general model because there's so much room for exciting work here. So I'm hoping to inspire you to think about the problem in full generality and not just the specific case that we can get a solution for. Okay, so these arrivals come online, right, one at a time. Each arrival is defined by we're assuming some set of true features, xt. That's like the email that the person really wants to send, but they may not end up sending it. They may send something else. Yt is their true labels, so let's say 1 if honest and -1 if spam. Okay, again, this is just the definition. I'm not saying that we observe these things yet. And they come with some utility function. Again, we don't observe it, which is a function of the classifier that's being used, the true email they send, and the email x hat that they end up sending, that they end up choosing to send. And their utility is a function of these things. So the utility for modifying their true email to the thing they actually send x hat when the classifier is beta. And what we'd like to think of this utility function as capturing is some trade-off, where I want to be classified as an honest email, but maybe I'll have to pay some cost for doing modifications. Okay, so there should be some trade-off in the utility. Okay, so if the label is 1, so if they're an honest agent, in this paper we assume that honest agents don't act strategically. Okay, it's probably possible to think of them as also acting strategically, but in examples like spam classification or detecting fraudulent transactions or something, we tend to think of these honest agents as non-strategic. So they just send the email they wanted to send. The spammers, the strategic agents, are going to choose this actual sent email in order to maximize utility, okay, in response to the classifier that's currently being used. Okay, so over these rounds, we deploy a classifier. The spammer or honest agent arrives. So this data point arrives. We've classified it. We get to observe its true label. And we'll measure our performance with some loss function. Okay, standard kind of machine learning approach. So this loss is saying, how well did we do when we deployed this classifier, when this observed email arrived, and we found out that its true label was this? Okay. Yeah. Good. Okay, and then we can update to some new classifier. The next email will arrive, and so on. Okay. Good. So that was a very general model. Now I'm going to give you a general way that we measure performance, and then talk about specific assumptions we make in our solution. So to measure performance, it's helpful to have this notation for the best response of the agent. So if they're honest, their best response to beta is to just send their true email, we're assuming, because by assumption, honest agents don't act strategically. Spammers, by assumption, choose this email x hat to maximize utility. Okay, so x hat of beta is the thing that maximizes utility. So the performance of our algorithm over these capital T time steps is just our average loss. Right? This is the thing that we want to be as small as possible. Okay, so it's the average over the time steps of the loss of the classifier we deployed, beta t, the observed email that actually got sent in response to that classifier, and the true label. Okay, so now what's our benchmark? So generally in online learning kinds of problems like this, you want to compare to the best fixed classifier in hindsight. So if I had known all of the agents that were going to be sending emails, and I picked the optimal beta star in advance and just stuck with it, how would that have performed? Okay, so there's a twist here, because it's not enough to just look back at all the emails we observed and say, well, you know, how would beta have classified those emails? because if we had deployed this different beta star, the emails we observed would have changed, right? They would have changed in response to this behavior. Okay. And so this is an idea that's very natural to this community, right? But I think in learning, these kinds of ideas are still becoming, still gaining ground in consciousness in how people think about learning problems in the presence of strategic behavior. Okay, so the benchmark we want to compare to is not how would some beta star have performed on the things we actually observed, but how would it have actually performed when people responded to it. So what would be the best possible average loss of some beta star, given that each arrival best responds to beta star, and of course the true label stays the same. Okay, so the difference between these is termed the average regret. Average meaning it's the per time step average. Okay, and the idea is that this should be going to 0 as capital T gets large. Right, so as we learn over a long time horizon, our performance should be approaching this opt that knew in advance what was going to happen. And we term this in the paper Stackelberg regret, just to emphasize this idea that it's this sort of leader-follower idea. So again, this best response idea. Okay. One side note, it's kind of interesting that the algorithm can't actually look at the data it has and compute what opt is, right? Because it doesn't know all the preferences of those agents. It just gets to see what the actual emails were sent. So it doesn't know how they would have responded necessarily. But under some strong assumptions, we can still compete with this opt. Okay, so let me tell you about those now. Okay, so for us in this paper to solve this problem, we're going to look at some very special case. So first, we're thinking of a linear prediction. So beta t is a vector in R to the d, and your prediction is beta dot x hat, the observed x hat. So a higher number is interpreted as a prediction of being very honest. A negative number, a very low number, is interpreted as a prediction of being spam. Okay. The loss function that we can consider is logistic loss. So this is a common loss function. So if your beta.x was very large and the true label was 1, then that's good and you have low loss, right? If they really were honest. If it was very large but they turned out to be spam, then you have a very bad loss, okay? And vice versa. And we can also extend these results to a hinge loss. Okay, both of these, if you're not familiar, are sort of convex softenings of the thing you might really care about, which would be like a 0, 1. Like if you classified them as honest and they were honest, your loss is 0. But if they were dishonest, your loss is 1. Okay, these are more computationally tractable. Okay, and we make some strong assumption on the spammer utility. Okay, so the spammer utility is going to be a positive minus some other cost component. And we assume this positive component is your prediction. So it's beta.x. So the more honest that you classify them as, you predict them to be, the happier they are. We interpret that as some higher chance of getting through the filter. But they have to pay some cost for modifying their email. Okay. So for example, maybe the true email they wanted to send was some spam advertisement, but they modified it a lot so that it barely mentions their product at all, and that pays a high cost for them. Okay. And we can solve this for a particular class of distance functions between the truth and the manipulation. The sort of largest example would be something like p norms of the distance between them raised to power strictly greater than 1. This matrix A here, you can also add that in, and that is mapping the features into some other space. So that gives you some more generality. Okay, so under these assumptions, we studied that general problem I told you about. Good. Okay. Great, okay. So the main results in the paper are showing how we can use online convex optimization tools to solve this problem. Okay. So existing online convex optimization algorithms, maybe with small changes. The key idea is to let this loss function, so consider this function LT of beta. I'm defining it to be the loss of beta when the agent best responds to beta. Okay, so now this is a function of just a single variable beta. It's a different function every round. We don't necessarily know all the details of it every round, right? We don't actually know this function. We can't write it down. But it's some function of beta. And the key point is that under our assumptions, this function each round is a convex function of beta. Okay. And convexity is very good for optimization. So that's the key result that we need to prove. Okay. Yeah, so I wrote down some of the main ideas here for those who are familiar with some of these terms. It's not a huge deal. But the main idea is some convex analysis, which may not be surprising when you write a function in this form. Okay, and so yeah, using some convex analysis tools, I don't think it's super important to get into. We can show that this function where we have the spammer's best response in there is a convex function of beta. Okay, and so that means we can treat this entire problem as the following problem. Each day we propose a beta, some convex loss function arrives, and we get to see what our loss was as a function of beta. We don't necessarily get to see if we had changed beta what it would have been, because we don't know all the details that led to this function, but we do know it's convex. Okay, and there are tools in the optimization literature that allow you to deal with that. Okay, so an example corollary by applying one such algorithm from the literature is that you can get this average regret, this Stackelberg regret I talked about, looking like order 1 over square root capital T, where T was the number of arrivals. So as time goes on, the difference between your performance and the optimal performance is going to 0. And that was the main goal. Okay, and we can, this particular algorithm has some really high dependence on the dimension D of the data points, the x's. And we can apply some other algorithms that do better in that respect, but maybe they get like a t to the 2/3 instead of square root t or such things. Okay, so I'll go ahead and wrap up. So some extensions that we spend a fair amount of time on in the paper. So one is an algorithm that can treat the honest updates and spam updates differently. So the difference is that if an honest agent email arrives, then you actually do know this convex function, and you can write down the whole convex function, right? Because you know that if you change beta, they wouldn't have changed their email in response. They're just an honest agent. That means that you get more feedback about this convex function. In particular, you know its gradient. Okay, and that means that you can just take a gradient update step. You don't need to use these more fancy tools for those update steps. But when a spammer arrives, you do need to use these more fancy tools. Okay, so we're combining both of those techniques into one algorithm. Okay, and we can treat somewhat more general agent utilities than the class I showed with the p-norm. There's some homogeneity condition that they need to satisfy, and the hinge loss as well as logistic loss. But the main idea is the same with this convexity. Okay, so future work. I'm really excited about future work opportunities in this area, although they seem quite difficult to me. So one is just thinking about other loss functions. Of course, like the 0-1 loss is very motivating, but maybe difficult. Other forms of agent utility. So again, we had this agent utility that was sort of very smooth and continuous. So the higher you predicted them to be honest, the happier they were. You might instead think of an agent that's, if they get through the spam filter, that's a good utility. If they don't, that's bad, a sort of very binary utility. That seems very motivating, but maybe difficult. And okay, for both of those extensions, maybe you need to go outside this paradigm that we're using, which is finding a way to just reduce to convex optimization and use those convex optimization algorithms. So it'd be really cool to just think of some totally different approach to these kinds of strategic classification problems. And of course, there's tons of modeling you can do as well, and different ways to model these problems. So that's it. Thank you. If you use what method? Oh, kernel method. Okay, off the top of my head, I don't see why you would lose convexity, but I'm afraid to make that claim. Yeah, I don't see why you would lose it. But, yeah.
If honest agents are also strategic, different utility,
I'm sorry, I missed.
if the honest agents are strategic
Yeah. Yeah, so if honest agents are strategic with different utility functions, I think we looked at that later and concluded that we probably could extend it because we probably could preserve convexity, at least with some assumptions on what they're doing. Again, as long as we have convexity, it's fine. Yeah, and there may be applications where that made sense, but we're thinking of applications where it didn't make sense to us that honest agents were acting strategically.